Welcome to our AI lecture series. Today's class is on Perceptron and Backpropagation Learning Rule, which is part 2 of our lecture series. So in our last class, what did we say? So we saw about single layer perceptron learning rule and also multi-layer perceptron learning. The single layer perceptron network is capable of classifying linearly separable data, which is using perceptron learning rule. And next one is multi-layer perceptron network, which is capable of separating even nonlinear classification, which is very useful in any complex function approximation and capable of solving any complex classification and regression problem. The fundamental learning mechanism under multi-layer perceptron is backpropagation algorithm. First, let us look into perceptron learning rule. How this perceptron learning rule helps to learn the single layer perceptron network and optimize the weight vector. So the ultimate goal of our learning mechanism is to optimize the weight vector towards the optimal combination of weights such that the prediction will be very accurate. So let's see how it works. So initially, there is an input vector and output value, so which is a data, so which is called as observations. The observation consists of input and output. So input is a vector which has multiple variables. Simplest example could be price of a house. The price of a house prediction would have all the input vectors, input attributes such as the size of the house, number of bedrooms in the house, number of bathrooms in the house, and the location of the house, zip code area of the house. So many factors would be there. So those are all the predicting factors of a house price. Then what is the output value of the house, which is the price of a house. So here in this example, the input attributes are given inside the next uh, network. That means the neuron in the network, which is actually doing two type of action. One is weighted sum, and then next one is activation function. So during the weighted sum, it's actually calculating the weighted sum of all these input values with respect to weight values, and then activation function is applied on the aggregated value, and it gives an predicted y. Predicted y is estimation of the house price. So initially, when the weight vectors are initially randomly assigned, the prediction may not be very accurate. The predicted value would be something else, may not be the accurate correct value of the house price. In our example, let's assume that the price of a house is around 400K, but this y prime, which is a predicted value or estimated value of the house price, is around 300K. Then do we rely on this output of this network? No, because it has a lot of error. So what we need to do is we have to measure the error and then update this weight value based on its value of the error. So what we do is here in the network computes error value, which is the difference between actual and prediction. Here in our example, it's the prediction is 300K and actual is 400K, and there is a difference of 100K error. That error value is again multiplied by its input value, which is one of the input value of the input vector, and then multiplied by its learning rate eta. So this learning rate and then input values are multiplied by its error value and then added back to the weight vector. So how it learns? The weight vector is updated in the next pass such that it's moving towards optimal value of the weight vector. The weights are getting adjusted based on the importance of those input value in predicting the output value. So this is how the perceptron learning rule works. But this perceptron learning rule works for linearly separable data. The application of this perceptron network and perceptron learning rules are in binary classification and pattern recognition. So this perceptron network can perfectly model linearly separable logic functions such as AND, OR, or NOT gates. And also, it helps to recognize simple patterns in data, such as simple shapes and signals in the data. Those are linearly separable. So next, we will move into next learning algorithm, which is a very robust and powerful algorithm called as backpropagation algorithm. So we also already saw that this backpropagation algorithm, specifically for neural network, was introduced in 1986 by the scientist Jeffrey Hinton and fellow researchers. So we'll look into how this backpropagation algorithm works. So here also there is a forward pass. During the forward pass, at the first hidden layer, the input values are aggregated using its weight vectors, and then activation function is applied. And this is the output of the first layer, L prime. And then this L primes of this hidden layers are inputted into the next layer, which is an output layer. Here in the output layer, again the same rules applies. That means there is an aggregated aggregation and then activation. Then Y prime is the activated output from the output layer. Now we here in the same example, let us consider the same example, housing price. We know the actual value and know the estimated value, and then we have to compute the loss function. Loss function is based on the difference between actual and output. And now the forward propagation has been completed. Next, what? We have to adjust the weights based on this loss function. How we adjust these weights? There is a beautiful mechanism which is called as gradient descent. So we will see how the gradient descents work. So there is a forward pass. During the forward pass, the estimation happens, and there is a backward pass. During the backward pass, that chain rule, that gradient of those weight vectors are computed, and the weights are getting updated, and then again the forward pass starts for with next observation or next example in the learning algorithm. So it continuously learns and adjusts its weights such that all the weight vectors are adjusted fine-tuned to predict that accurate value of a given task. So now we will see how this learning algorithm works, that backpropagation algorithm work. So this is the simplest network view. It shows how forward pass and backward pass works. Let's move into how the intuition behind the backpropagation algorithm. So let us consider that a person standing somewhere here in the hill. So now his objective is to reach the land, that means ground surface, and then pick up this truck. So how he would reach this ground? We all know that it's very simple. We need to climb down from the hill towards this optimal point. This is the expected point where this person needs to reach. So also when we observe that completely three-dimensional view of this hill, we know the direction in which the person needs to climb down, and also the step size, that what would be the step size and the direction, and slowly he will walk and then climb down and the hill. So here, what is the two major actually concepts being applied? We don't realize that what concept our brain is applying when we climbing down from the hill, which is actually looking at the ground and where we are, looking at where we are, and then understand the slope of the hill with respect to the local point. When we look at this blue point here, that person would measure, or we, when we climbing down, we measure the slope at this particular point and the direction of that slope, and also we look at that step size, that how far we need to take our step so that we will be safer enough, not falling from um, this mountain. So we slowly take one step at a time, and then find out that correct direction by measuring the slope and moving towards the correct direction, and we'll reach that ground surface. So how we apply the same mechanism in our neural network? So how we mathematically model this simple mechanism of climbing down from the hill? So let's see this simple function. So here there is a simple function which is f of x equal to x minus 2 square plus 1. So this is how the contour looks like. Now we know the optimal point, the minimal point, the ground point, or where the error is minimum is this one, 2 comma 1. So we are somewhere here. Let us assume that the person is standing somewhere here. So now how this point will get moved towards this, its optimal point, towards 2 comma 1, just by looking at the gradient, that means slope. By measuring the slope will give the direction of movement. So when we measure the slope, that means first we take the first derivative of this function, it gives the direction, and also we measure the step size in x direction and y direction. So in x direction, to reach this point, what would be the size? We need to take minus 2 step towards the left hand side, and at y direction we need to take 1, 2, 3, and 4 steps at the downward direction. And we take that step, then obviously we reach this optimal point. So we may not be able to take a very big step, or the next time we can just take the smallest step, that means one unit in y direction, and one maybe another half unit somewhere here in the x direction, and reaches this point. And slowly we can climb down. Mathematically the function can reach us slowly towards its optimal value just by taking the gradient and first derivative, and also moving in a right direction by looking at the slope. So this is how the backpropagation and gradient descent algorithm works. So here, once we compute the gradient, then what we do is, gradient means first derivative with respect to the loss function at each and every weight connection. So calculate this value applying this first derivative rule and chain rule, partial derivative and chain rule. We compute this value and then multiply it with this learning rate, and which gives the quantity at which we need to update the old weight. So the new weight will be the old weight during the previous iteration, and then add or remove this much amount from this weight vector based on the importance or gradient of that particular uh, weight connection. So this is how the radium algorithm works. Finally, what happens, this is a physical example where a single person climbing down from the hill and reaching the ground surface by looking at the slope and direction on the step size. In the same way, when we apply this analogy into mathematical functions, this is a contour plot, three-dimensional view of this loss function graph, where uh, maybe the two directions x and y might be the weight vectors w1 and w2, and the third dimension could be its loss function L. So look at this example, how beautifully the balls rolls towards its uh, optimal value by looking at the direction and the movement, and it reaches finally the minimal points. This is how the backpropagation algorithm works. So this is a 2D contour map. The 2D contour map, wherever the starting point is, it slowly moves towards its optimal point, and after some iterations, it reaches its final value. This is how the backpropagation algorithms work. Thank you for watching. We will continue our lecture series in our next class. Thank you again.